In the operating room, the anesthesiologist walks a narrow physiological line. Deliver too little anesthetic, and the patient risks intraoperative awareness. Deliver too much, and the resulting hemodynamic instability can compromise perfusion to vital organs. To ensure unconsciousness, the gold standard is monitoring the brain itself, using a 16-channel raw electroencephalogram. However, the resulting data is a highly complex web of electrical waveforms, requiring specialized neurological expertise to interpret in real time. The practical clinical solution is the use of quantitative depth of anesthesia monitors, such as the bispectral index or spectral entropy. This graphic shows how these devices take highly chaotic, multidimensional neural data and compress it into a single dimensionless number. To understand what this output actually represents, we have to rebuild it from the ground up, starting at the cellular level and ending with the mathematical algorithms that render the final score. Treating this index as absolute truth without understanding the underlying biology leaves the clinician blind to the monitor's critical limitations. The electrical signal we are measuring originates in the superficial layers of the cerebral cortex. A common misconception is that surface electrodes are reading the firing of individual action potentials. They are not. This model shows that the EEG actually measures the algebraic summation of postsynaptic potentials, both excitatory and inhibitory, occurring in the dendrites of pyramidal cells. For these microvoltages to be detectable, there is a strict anatomical requirement. The pyramidal cells must be oriented perpendicular to the cortical surface. Because millions of these cells are aligned in parallel, their simultaneous postsynaptic voltage changes generate sufficient extracellular current flow to reach the scalp. These minute current flows are what non-invasive adhesive electrodes detect when placed on a patient's forehead. The resulting signal is incredibly fragile. The electrical potentials recorded in an EEG range from 0 to just 200 microvolts. The raw continuous waveform displayed on a monitor is simply the algebraic sum of billions of these microscopic cellular conversations happening simultaneously. This diagram illustrates the baseline electrophysiological state of a healthy, awake patient. The waveform is asynchronous, featuring a low amplitude and a high frequency. This high-frequency chaos occurs because different regions of the brain are actively engaged in independent neural processing. Alpha waves appear during relaxed wakefulness when a patient's eyes are closed, originating primarily from synchronous activity in the parieto-occipital cortex. When the patient opens their eyes or concentrates, this synchrony breaks down in a process called desynchronization. The alpha wave morphs into a beta wave. Beta waves cycle at frequencies greater than 13 Hz and present with very low amplitudes, typically under 50 microvolts. This rhythm characterizes active mental concentration and arousal and is highly prominent in the frontal regions of the brain, where anesthesia monitors are placed. As a patient descends into anesthesia, the fast beta and alpha rhythms are replaced. The cortex becomes heavily synchronized, producing low-frequency, high-amplitude theta and delta waves. For a machine to measure depth of anesthesia, it must automatically detect this exact shift, the transition from high-frequency independence to low-frequency synchronization. Analyzing a raw frontal EEG trace visually in real time is nearly impossible for a clinician due to the sheer density of the electrical noise. The data must be translated from a time domain, which shows voltage over time, into a frequency domain. This diagram demonstrates the foundational mathematical algorithm used by modern monitors, the fast Fourier transform. The fast Fourier transform decomposes any complex, chaotic waveform into its constituent sine waves, separating them by their specific frequencies and amplitudes. Once separated, these individual sine waves are mathematically plotted onto what is called a power spectrum. By squaring the amplitude of the individual components, the data is reorganized into a chart plotting frequency against power. This power spectrum explicitly reveals the dominant physiological rhythms that were previously hidden within the chaos of the raw time domain signal. The fast Fourier transform acts as the mathematical translator, converting biological electrical noise into a highly structured dataset ready for algorithmic scoring. This illustrates the divergent pathways in modern monitoring. Different manufacturers apply different proprietary mathematics to the exact same Fourier data. Following the bispectral index, or BIS pathway, the algorithm measures frequency and power, but also calculates the specific phase relationships between sine waves. Using a proprietary logistic regression algorithm derived from a massive healthy volunteer database, it compresses these variables into a simple scale from 0 to 100. A BIS value between 40 and 60 indicates surgical anesthesia, while numbers approaching 0 indicate profound cortical suppression. The spectral entropy pathway takes a different approach, applying a Shannon probability function to the power spectrum to measure the level of disorder within the signal. The logic here is thermodynamic in nature. An awake brain is highly chaotic and unpredictable, yielding a high entropy score. An anesthetized brain is ordered and synchronized, yielding low entropy. Both methods share a major physiological confounder: electromyography. Electrical activity from facial muscles in the forehead overlaps perfectly with the high-frequency bands of an awake EEG. To account for this, the spectral entropy output splits into two distinct indices: state entropy and response entropy. State entropy analyzes a narrow frequency range from 0.8 to 32 Hz, strictly capturing cortical EEG. Response entropy extends that range to 47 Hz, specifically to capture facial muscle EMG. If the response entropy number rises significantly above state entropy, the monitor is detecting frontalis muscle activity before a return of cortical activity, providing a crucial early warning of inadequate analgesia. Although these algorithms provide a consistent method for interpreting EEG data, they remain statistical proxies derived from healthy volunteer databases. They possess specific pharmacological blind spots. For example, ketamine causes paradoxical high-frequency cortical excitation, confounding processed algorithms and generating falsely high awake values. Nitrous oxide also fails to produce the standard slow-wave delta pattern, rendering the index unreliable if utilized as the sole anesthetic agent. Furthermore, external artifacts like surgical diarrhythmy or unrecognized baseline EMG can falsely elevate the number, suggesting patient awareness where none exists. We have traced the signal from the microscopic postsynaptic potentials of pyramidal cells through the mathematical prism of the Fourier transform to the final dimensionless index. True anesthetic vigilance requires looking past the single number on the screen and maintaining a foundational understanding of the underlying neurophysiology that generates it.